Well, hello friends, welcome back to the program. Today we are going to continue working on our JIT compiler in libjs. And the first order of business is that somebody named Jeffrey opened a pull request saying, hey Andreas, I just watched your video and since you mentioned multiple times that you didn't want to implement throw yet, I figured I would. Writing a JIT from scratch is very interesting and I love following along watching your SerenityOS devlog videos. Hope this helps. So Jeffrey has gone and implemented the throw keyword here, and I figured we should start today by merging this change. So it ends up being very simple now that we have the check exception primitive. So the compile throw here really just has to load the accumulator into GPR0 and then copy that into the exception register, and then immediately do an exception check, which will then trigger the throw, either jumping to the catch or returning from the jitted function. And yeah, it's just the boilerplate plus that. So that's looking very good. And then we have some unrelated gunk here, which really shouldn't be in the change. But since we are on a experimental branch here anyway, I'm just going to take it as it is. And wait, why does everything look so weird? This is not the UI that I'm used to. I don't want to make a merge. I want to rebase and merge. Jeez. Yeah, everything's all different here. Okay, thank you, Jeffrey, for adding that. And let me just pull. No, what did I want to pull actually? Okay, no, mine lib. Spelling. Okay, there we go. Okay, we are back on track. So that's cool. Now we can use the throw keyword. Anyways, with that out of the way, today I thought we would do function return values and basic arithmetic. So I would like to be able to implement, like to be able to write JavaScript that adds numbers together, multiplies them, divides them, and then returns them. So arith return, let's call it. And we will have a jitme function here that takes maybe 3 numbers. What do we think about that? And then return a plus b times c. Maybe like this even. Okay, and then we can log the result of calling this with 2, 3, 4. And that should then print 20. No, that's not how you do that because I didn't call it. Pardon me. Okay, let's try that again. So yeah, so V8 says 20 and we would say 20, but we do fail the JIT compilation because we don't have support for the add op yet. If we run with bytecode dumping, we can see that we end up with some new opcodes that we haven't added to the JIT yet. We have add and mul and also return. So let's get cracking on implementing those. So for starters, they're really just going to be, in the case of add and mul, they really just need to be native calls at the moment, since we have to call out to the helpers in libjs for adding values together. Those are in value CPP here, yeah, because there are all kinds of interesting rules about adding JavaScript values, and it may throw exceptions and so on. We do have a fast path here in the C++ version, as you can see. If both values are i32 or double, we can do a direct addition without type conversions. And we also know that it doesn't throw in that case. And this kind of fast path would be great to implement in inline assembly eventually. But I'm kind of, we're going to skip over implementing all the fast paths in the first paths here. So let's see. Let's go back to the compiler and just add the compile add and compile. I guess we can do subtract and multiply and divide. Yeah, let's do all of those fellas. And maybe I will even expand the test case here to take DE. So we divide it by D, and then we minus E. Okay. So that gives us -2. I hope that V8 would say the same thing. Yeah, so let's make the JIT arrive at the same result. Okay. So let's see. Compiler. Compile. Okay. So first, we're just going to add them to the big switch here. We should probably generate this switch with a macro or something eventually. But right now, I'm just typing it all out or tabbing it all out, letting Copilot do the heavy work. Okay, there we go. And then we can jump straight to implementing these little fellas. Compile add. Okay, so the binary expression ops like add, sub, div, mul, all of them have a left-hand side op, left-hand side register, and they use the accumulator as the implicit right-hand side. So we can kind of do what it's suggesting here, except the right-hand side is the bytecode register accumulator. So we load the left-hand side register into argument 1, accumulator into argument 2, and then this is wrong here. We don't want to add them together, although it would be lovely if it were that simple, but actually we have to make a native call. So we have to call not value add. We have to call our very own helper, which we will call cxx add. I guess that's what we've been calling the ones we've added so far. So cxx add VM. Yeah, exactly. Left-hand side, right-hand side, try or set exception, and it just calls the add helper. So that's the one that we just looked at here that has the optimization. Right, and here there's room for the fast path here. So the way we would implement the fast path later, the way we will implement it later, is by emitting code that does these kind of checks, like verifies that you're adding together two int32s and or two doubles, and then adds them together with assembly code without calling out to C++. But right now, let's just focus on adding these. So I think we can do, they're going to follow the same pattern here. So I think Copilot can sketch it all out for me. I would imagine void compiler, compile sub. Yep, there we go. Beautiful. And then we do mul. And exactly. And finally, we do div. Okay. Yeah, that's looking great. And that gives us all of those, but we still need return. So let's see. I don't think I can compile this yet, right? Yeah, unsupported bytecode op return. So I still need the return. Let's add that as well. Although let's commit here first of all. JS, JIT, add, support for add, sub, mul, div, opcodes, or bytecode ops. Okay. Now we just need a return. And return works on the accumulator as well, as I recall. I think it does. Right, yeah, the accumulator is the implicit return value. And we can see that what we do in the interpreter, bytecode interpreter, is that we call doReturn, which then puts the return value into a special register and clears the exception. Interesting. I don't know why that's necessary, but there might be a reason. But I think what we want to do is we just want to set the return value into this thing and then exit out of the jitted code, basically. And then as a fix me, we should call, we should jump via finally block if there is one in effect, but we don't have to do that right now. So let's see how we implement return. Void compiler, compile return. And let me just put a compile return here. Okay. It's going a little bit faster than I was expecting. So exit is good, but we also need to put it into that register. So store VM, or let's load the accumulator into GPR0. And then let's store VM register, return value, GPR0. Yes, exactly. So, and then we exit from the compiled code, and let's see how that goes. Well, the end result is 2, which is not ideal. Our inputs here look a little suspicious. Wait, what's going on with that? Arith return 2, 3, 4, 5, 6. I would have expected the locals to be 2, 3, 4. 2, 3, 4, 5, 6. Interesting. So probably we're screwing something up. What if we don't call out? That's very odd. So what if I just pass 2? Local number 2 is 2. What? Okay. Local number 3. But what is local number 1? It's the 4th local. What on earth? I am so confused. How is that happening? Okay. So maybe they're not assigned in order. I guess if they're just, we're probably just setting them up with a hash map. I always just assume that they would be in order, but I guess they might not be. Local. Wait, who adds these locals? Function parameters, candidates for local variables set. That looks like a hash table. Okay, yeah, so I guess they're just ending up not ordered. Maybe we could make it ordered by doing that, but okay. Let's not get distracted with this. It's fine if they're not ordered, as long as it works correctly. I was just very surprised. But since we're not getting the expected result, let's make something simpler and take it from there. So maybe we'll do this. Add. Return a plus b. Console log add 2, 3. That should give us I would have expected something other than, oh shoot, there was a %0 this entire time. I wasn't even looking at that one earlier. Anyways, let me send it to out. Okay, so 2 and 3 are the inputs, but the output is 2, so that's not correct. Get local 0, store it into register 5, get local 1, and then add the accumulator with what we stored here. Bytecode looks fine, but we're not adding it correctly. CXX add. Okay. Am I forgetting something about the way that we did native call elsewhere? Native call. Oh, the return value from the native call. I'm just assuming that it would be in the I'm using the wrong register here. I'm using argument 1 and storing that into the accumulator. I should be using the return value register. So that was all bogus. Okay. Good. And now we get a 5. That's great. And if we call jitme, the original thing, we get -2 as expected. Okay, so now we're actually doing it the right way. These guys also need check exception, by the way. So let's make sure that we do that for all of them, and then we'll just fix up the previous commit. Okay. Oh, I can't. Let me just do that while I fix up the commit. While I amend the previous commit, I should say. All right, and then we bring that back. And that is our return. Support the return bytecode op. Very cool. Now we can return things. And we should also be able to handle exceptions if somebody tries to add a number to a symbol or something like that. Let's try it. Weird. So return s+1, and we'll call weird with a symbol. Yo. Which should throw, and it does throw. That's great. So that just works. Our exception check seems to work. In fact, let's see that try works. What we added last time, that should also work. What if we return from here? Return 6, or good and bad. Can we do that? Oh, we can't because we don't have new string. Well, let's implement new string. How hard can it be? Okay, let's do new string. So new string just creates a new string, like allocates a new string literal and puts the string object in the accumulator. So that should be fairly straightforward because we just have to call out to C++ again. So const op. Although it'll be interesting how we do that. So we have an index into the string table, and the string table is part of the executable, the bytecode executable. has a string table right here, and the string table has a vector of strings that we can then get from it. All right, so in order to get to that, we need to write a, it's not going to be unused, but we need a cxx new string. And in order to get it, we want to do like primitive string create. But I mean, the bytecode executable is always going to be there. As long as we have jitted the code, we can count on this to keep everything alive because we're executing it. So I guess we could take pass a pointer here. So like it's a deprecated string. We can pass it like that, and then make this thing call it. Do we know the executable? We have the executable here. Okay, I think I'm gonna have to tell the compiler about the executable so that it knows. Compiler, compile, blah, blah, blah. Bytecode executable. That's just gonna be a const reference, apparently. It should probably be eventually it should probably be a mutable reference now that I think about this, because we put stuff like inline caches in the bytecode executable. So maybe we'll just do this here. Let's see if the code would tolerate that change. Not sure. We'll see. Compiler. This thing doesn't have a constructor. Okay. We'll add one. Thank you. For now, we can just do that. And then we'll be good here and there. And new string. All right, so now we need to expose the string table index. Okay. String table index is just a strongly typed integer. So we have the index right here. Const string is m bytecode executable string table get index. So something like this. Okay. And then we want to pass that in a native call to this fella. So not exactly what I had in mind. I want to bitcast to U64 the address of string. See, I can do that, right? Yeah, because it returns a const reference. So that should be okay, I think. And then we call native call to cxx new string. Put the return value in the accumulator, and at that point, I think we're good, because this is not a throwsy operation. Creating a string from a literal cannot throw. So we don't need to think about that. And let's see if unsupported by, oh, I never added it to the list. Okay, it makes the string good. I wonder, let's concatenate two strings. What if we get them like this? This will be interesting. Console log hello friends. Maybe we can even do this. Actually, we have to do that to get a new string bytecode instruction inside the woo function. So let's try it. Hello. Wait, I'm making the mistake again of not actually calling the function. Here we go. Concatenated. Oh, that's so cool. All right. So let's take a look at the assembly for that new string operation. Should be really, really simple, right? Because it's, yeah, we're just loading up arg1 with a pointer to that string as it exists inside of the bytecode executable string table, which of course is a runtime allocated pointer to a string. Is it this one perhaps? Seems plausible. So that's a pretty cool thing where in the JIT, we have the ability to take like things that were allocated at runtime, and we can put their actual address into the instruction stream. So that's a sort of an interesting advantage that we have over compile time code, where in C++ here, it will be much harder for me to get the pointer to a string like this and be able to pass it as a constant. So that is pretty neat. Oh, that is very cool. Okay. Okay. Very excellent. Right. So I'll just say here, JS JIT support the new string bytecode op. This necessitated making the JIT compiler aware of the current bytecode executable, since that's where all of the strings are held, string literals are held. But that seems like a good thing. Yeah, that's so neat. Now I kind of want to do a bunch of other binary ops. Maybe we can just do like all of them, because here we have a whole bunch, and it almost makes me feel like we should be able to use this macro to write out all that code. Can we do that? To write that code that we had for all of those? We don't have to repeat ourselves so much, because this is how we implement the bytecode interpreter for all of these binary ops. Binary op, by the way, just means that there are two sides, so like a left hand and a right hand side, just to clarify. Yeah, let's try that. So instead of, well, this will be the template for how all of them should work essentially. So we'll make a macro that instantiates these two functions. We'll call it X or do binary bytecode op. Okay, something. I don't know. I just have to call it something. And then we have the title case name and the snake case name. Okay. And then we are off to the races. So let's see how we do this. Start by just doing this, I guess. Why is this so? Why am I making it so hard for myself? Okay, here we go. And then we put the snake case name here and here. And here goes the title case name. I didn't need the pound there. Here I will need the snake case name. Cool. Okay, so let's see. What was it called? JS enumerate common binary ops. Do compile binary bytecode op. That's kind of interesting. And then I should be able to yeet all of these guys. And what is my mistake now? Expected semicolon after top level declarator. Okay. Sometimes I feel like it's easier to just run the compiler and see what it gets mad about. 338. Oh. Wait, what's wrong with that? I am confused. So that is fine. Well, one thing that we have to do regardless, we're going to fix that in a second, but we also have to deal with this in the compiler.h here. Do compile common binary op. Yeah, let's call it that. And these are just going to be like this, like that, exactly. JS enumerate common binary ops. Am I using this wrong? Class member cannot be redeclared. I mean, that's fair. Because we probably have less than from earlier, right? So less than, yoink, and then we're good there. Okay. And we need to get rid of less than here as well. It's just a binary op. Okay, and let's use the same name here. Do compile common binary op. That was a pretty catchy name. And oh, this thing is wrong. Snake case name. Why am I failing at this simple task? I apologize to anybody who's watching right now and you're just seeing exactly what the problem is and I'm just messing it up. Macro redefined. Well, I thought I undeffed it. But I didn't. That's the one I wanted to undef. Okay, a replacement. Oh, shoot. Wait, I'm pasting my preprocessor tokens as strings. That's not what I want to do. I want to paste them. I want to concatenate them onto the identifier. Dang it. Is it just me forgetting how to use the preprocessor? CXX abstract equals. wait, oh, abstract equals and typed equals. So those are missing. We need to invent those apparently. How's that handled? How does the interpreter deal with that, I wonder? Oh, those are just in the interpreter.cpp. That's a bit annoying. So I guess we should probably move these out somewhere where they can be used. For now, I'll just copy them into here. And does that solve our entire problem? Yes. Okay, so that's interesting. So now in theory, we have support for all of these binary ops. That's great. And did we end up with less code? Yes, 31 insertions, 61 deletions. So we made the implementation less repetitive. Node.js, JIT, support all the binary bytecode. Binary bytecode ops. And use the X macro to avoid repeating ourselves. That's cool. That is very, very cool. Wow, we've suddenly added support for so many things. Makes me wonder what else we could add. I kind of want to just throw a program at it and see what doesn't work. So let's go to the we can go to the SunSpider benchmark suite, which is like these old JavaScript benchmarks. And what if we just throw like, I don't know, crypto AES at it? It fails to compile every function, right? Of course, because we're missing something that's used everywhere. But if we look in that file, I feel like if we eyeball this, we should see some function that is like stupidly simple. Got array access. This is complicated. Let's just look at the functions. It would be cool to have a function that does something small and simple that we could actually handle. Got like object property accesses and stuff. Maybe it was a little overly ambitious. Then again, why couldn't we just implement some simple property access? So what do we have here? Let's see. 3D. I just want something really simple. Creating arrays from literals. Oh man, there's so many things we're gonna have to do. I guess, all right, fine. Let's just implement simple object property access. So property access. Get x. Oh, return o.x. Okay. Something like that. Get x test. So we don't support the bytecode op get by ID. That is object property get by identifier x here. Outside of that, I feel like, yeah, everything else should be fine. So we just need to implement that one thing. And again, that is just going to be a call to C++ right now. And then in the future, we could do fancy inline assembly to do better things. But presently, let's just do it as a call to C++. Okay. Oh, wait, back up. I'm forgetting something. I'm in the wrong directory. I'm forgetting that here we need to actually call the appropriate compile functions for all of those binary ops. So less than all of these guys. Okay, so define do compile common binary op. Sure. Okay, title case name. And here, snake case name. Do that, and we can even put it the very last, since it's a bit weird to have this macro-y stuff. Okay. Yeah, that actually makes the previous commit even smaller. Okay, so let's get back to property access. See how that would look like. Get by ID, right. Get by ID. Thank you. And then okay, so get by ID is another interesting one. So let's see what it needs to do. So get by ID, we have the object will be in the accumulator. So if we look at the wait, where did I put that? Wait, now I totally forget where I put that file. In the SunSpider directory. Okay. Let's come back to the comfortable Serenity build directory where I normally like to hang out. Okay. So this thing, what it will do, it loads the object into the accumulator here. So we have O in the accumulator, and then we do get by ID, and 0 here refers to the identifier table. So it uses identifier 0, which is X. So we have accumulator.x basically is what this thing does. And it can throw, and the identifier is in the executable, bytecode executable. But I think we could do the same thing as we do for new string. We can kind of do the same trick where identifier is bytecode executable, identifier table get. Does that thing have a name? Maybe it's not exposed. There's no API, but it's here. Property. Right. So now we have it as property. So we get that, and then we have a deprecated fly string pointer that we can just pass to our new friend, which is going to be cxx get by id, and it will take a base and a property, I suppose. Is that enough though? I feel like if you look at the bytecode interpreter implementation, it calls a helper called get by id, which does more stuff. And at this point, we definitely want to call this thing the same thing that the bytecode interpreter calls. And now I'm starting to feel like we need to put these in a place where both JITted code and the interpreter can use them. because it's not good that they're hiding here in the interpreter CPP for this kind of stuff. So we need to call these something. I guess they're part of, I mean, they're not bytecode, or they are, I guess they are kind of bytecode helpers. Like implementations? Common implementations. I don't know. We'll call it that for now. It's not the best name in the universe, but it's okay. Common implementations. Sure, whatever. There's definitely a better name for this, but we'll suck it up and not get bogged down with sweating the name of this thing. So these will be in JS bytecode, and yeah. So we should probably lift the, I was going to lift the copyright from this file. So I guess we'll do this. All right. And then we want to put this guy here. Okay, bytecode. And we might not have a bytecode interpreter to throw at him, actually, or I would prefer not to. So let's see if we can just throw the VM. Where does this thing come from? Identifier table.h, sure. Okay. It seems like a fair enough thing. And can we just do the VM here? I wonder. I mean, actually, actually, maybe we can leave it as interpreter. Yeah, let's just leave it at that for now, and then in the future we can switch it to VM. Just in the interest of changing as little as possible here. Base object forget, we apparently also need. So let's bring that with us. That looks like a helper function used here. This guy should not be static. Okay, now you have your fancy base object forget friend. You're good. And this thing needs to include the common implementations. Okay. Then somebody else calls base object forget get by value. Okay, so that's fine. We'll just expose this. Or we'll just add it to the header as well. That's okay. And then maybe we can even fix me. Or no, that's okay. That's fine. Whatever. So, what we want to call is from the common implementations, get by ID, bytecode get by ID. We can get the bytecode interpreter, the property, the base value. Oh my goodness, we need so many things here. So what did get by ID pass to this fella? Passes the base value twice, and then the cache index. So the cache index is the index into the executable set of inline caches for this property access. So we will remember information about this property access, and then subsequent subsequent executions of this instruction can be faster because they have cached metadata about the property access. So that we need to make sure that that gets passed along as well. And I guess when we're generating code, we know that, so we could pass the cache index. Let's see, what are we passing here? We're passing the base, the property. Base we're going to use twice, and then we need the cache index as well. So the cache index is going to be, what was that? Just a size t, right? Or something? A U32. Okay. Okay, so how do we pass all this stuff? We need to pass one more thing. A U32 cache index? I mean, we decide what we want to pass here. Oh, what's wrong with this thing? Property. Oh, right. The property is going to be a deprecated fly string. Or no, it shouldn't be because he does the lookup for us here. Okay, well, there's definitely an opportunity here then to do the lookup at JIT compilation time instead of doing it here. So that's a future optimization, let's say. Let's not worry too much about that kind of stuff right now. There will be plenty of opportunities to comb through this later and do all kinds of micro goodness. Okay, you're not liking this either? What does that thing return? Throw completion or void? Oh, I see. It doesn't have a return value. That's a bit odd. Get by ID. Oh, because it sets it in the accumulator. Oh, that's interesting. Okay, all right. So I guess we just do that, and then we don't need to return anything. So this can be void, have no return value. It's making a mess of this. Okay, maybe I should change how get by ID works, because now it's getting a little bit frustrating to work with it. So let's make it return the thing instead of poking into the accumulator. So here it would return the thing, nice and tidy. Here it will return this. And here, return value, or just value, I suppose, is fine. Okay, and now nobody in here looks at the accumulator anymore. So that's good. Then we can change the way we call it from the interpreter. So we would say like interpreter.accumulator, something like that. Okay. That should be good. Okay, now that we do it that way, let's see. So we want to make a native call here. Want to load into arg1. We want to have the base value. So that is the accumulator, actually. So arg1 should be the bytecode register accumulator. That's the object that we're loading from. And then arg2 is going to be the property. And the property, how can we get it out? Dot value. Yeah, that's the integer, corresponding integer of the identifier table index. And arg2, and then arg3, is going to be the cache index. So arg3 cache index, and we haven't actually, did we not come up with arg3? Arg3, is that R8? Wait, is that true? Let's see. Calling convention. 1, 2. RDX, RC. Why are you guessing RCX? That should be RCX here. Come on, bruh. Okay. And then let's expose the cache index so that we can get to it. All right, will you compile? Not exactly. 373, this function does not return. Oh, yeah, right. But now it will, because we changed it so that the helper returns the fetched property. Okay, we're back on track. Now we got to make the native call to get by ID, and then put the result in the accumulator, the return value, and then do an exception check here. Yeah. And that should be, I think that should be it. Oh, we have to actually add the common implementations thingy to the CMake list. Bytecode. Okay. Oh, failing assembler.h 152. What am I trying to do? I'm trying to mov something that he doesn't like in compile get by ID. Okay. What am I moving that you don't like? Oh, is it the moving M32 here? Well, I'll just use M64 then. Whatever. No big deal. I'll just be zeroed out in the top bits. And look at that. It works. We're getting 1, 2, 3. Just like we should be. That's really sweet. So now we can do property access at least. Very awesome. Yeah, property access. And there's so many other things to do. I think we could just go on forever, but we have to stop at some point. And we did a whole bunch of things today. We did return statements. All the binary ops are now supported. Getting object properties now supported. So that's good. And let me go ahead and do that. Just splitting them out into a separate file first. libj. So that we have that as a separate commit. Missing pragma once, you're right. I'm sorry. Begin moving shareable JIT interpreter stuff to somewhere. Yeah, there are a lot of native C++ functions that will be used by both the bytecode interpreter and JITted code. Let's put them in the their own file instead of having them in interpreter.cpp. Okay, and then get by ID. Support the get by ID bytecode of. Okay, now do basic property get access in cheated code. That is super sweet. Very, very sweet. Okay. I'm just going to stop here because there will be no end to this otherwise. I think we've established a good set of things here. We've figured out some patterns for how to progress, especially with sharing code between bytecode interpreter implementations and jitted code. So we'll put that in the common implementations. Actually, the stuff I copy pasted for equality should probably go there as well. These things, I'll put those in common implementations right here. And maybe I'll even do this. And abstract in equals and whatnot. They can be inline functions there because they're very, very simple. Let's see. Oh, wait, then I would have to say bytecode : : Okay, well, that was too hasty. Let's end where we ended. And I'll have to come back to that. But yeah, this is the end of today's video. If you made it here, thanks for watching, for hanging out. Making good progress now on the JIT compiler. And I don't think it will be terribly long before we will be running some simple programs, and then we'll be able to throw some benchmarks at it, see where we're at sort of, and start identifying interesting bottlenecks to make fast paths for. It's an interesting road ahead, but I'm having a lot of fun with it. I hope that it's interesting, educational, and yeah. I'll see you next time. Bye.